Okay, so this week we're going to get into wind and weather to a point. Uh, Wind is really the motion of air. So we've talked about temperatures, how they move from place to place and change. We've talked about moisture. We've talked about pressure and its changes. Well, how does the air from in Ohio get to my house down here in southeastern Virginia? Or how does the air from the Gulf of Mexico get up to Ohio? Well, wind is what carries the air around. So we got to understand wind. So let's take a look at wind here. So what are some of the forces that control it? Well, it's motion of air relative to the Earth's surface. We all live on the Earth. So a force is something you apply to an object that pushes it, makes it begin to move. Say you throw a baseball or get your car moving. There is an acceleration that takes place with that. That's a force that is being applied. And the force is equal to the mass of whatever that object is times the acceleration of it. Well, there are several forces that act on air. And we're going to go over each one of these. So first off, isobars. The more closely spaced an isobar is together, remember, the Earth does not like pressure gradients. It's going to try to eliminate them. And if you think about it, high pressure weighs more than low pressure. So it's all that higher pressure air is going to try to move to where low pressure is and get rid of it. So the closer the isobars are to each other, the greater the slope, you could say, downhill that air parcel is going to want to travel. So let's look at that just for a second. I really want to show you something here a minute with Ian. There's Ian. I am going to blow this up a lot. All right. So I just went crazy here. But I wanted you to see Ian and the pressure gradient it has. All right. Can't really see a whole lot. This outer one here is 1,012. Here is 1,008. Here is 1,004. So from this 1,004 to the center of Ian, that short distance, we're down to 937 millibars is what that center is. Think about that pressure gradient. We're talking what? A pressure drop of 70 millibars in probably a couple hundred, 100 and some miles. Now, take a look at today's analysis. We're going to jump back out of this, back to normal. Here we have today's analysis with a low pressure, 1,008 millibars. We have a high out here, 1,038 millibars. 30 millibars, but thousands of miles across. That pressure gradient compared to Ian, nothing. But yet, look at what the winds are. They're 10, 15 knots up here by the little tighter gradient, maybe 15 to 20 knots. So pressure gradient has a huge impact on winds. And as you just saw, there can be major differences in the amount of pressure gradient. Yes, nor'easters, major wintertime lows, do have a decent pressure gradient, but nothing like a hurricane. That's why their winds may get up to 50 mile an hour, 60 mile an hour sometimes, maybe even 70 mile an hour. But nothing in the way of a pressure gradient like a hurricane has. So now you can see here the tightness of the pressure gradient across these isobars. So let's go on from here. What's some other forces? Well, when you drive a car, and you're going around a curve, what keeps you in that curve? Why don't you go flying straight? Some force is making you go around that curve. What's that force? Well, that force is centripetal force. As you can see here, when you're pulling a ball around, like if you did a hammer throw, you are pulling inward. There's a force always directed into the center. And that's what's holding you in the curve as you go around. And it holds wind in curves path too. So there's another force acting. We have a pressure gradient force, and now we have a curved centripetal force. And interestingly, centripetal force is not independent. So if you were to get rid of it, you'd go in a straight line. There's another force, because the Earth rotates. The Earth rotates, and because of that, near the equator is rotating much, much faster than up to the pole, where it hardly rotates at all. And because of that, if you keep looking down at a certain perspective on the Earth, here would be a point, and here, a couple hours later, would be the same location at that point. Notice there's a bend to the right with that. Coriolis force causes air to turn to the right in the northern hemisphere and turn to the left in the southern hemisphere. So here you can see the deflection. Finally, we have friction. Down near the Earth's surface, along the ground, for example, there's a roughness there, maybe a mountain range or whatever that's slowing the air down. That's all friction and turbulence. Now, over water, water's fairly flat, so not as much friction. Again, here's another component of force. And this only is near the surface of the Earth. Further up in the atmosphere, you do have turbulence, which is a form of friction, but not to the extent that you have it near the ground. Gravity is another factor that pulls on it. It only impacts air motion in the vertical, not the horizontal. So if you're pulling things down with gravity, it will pull air down towards the Earth. Oh yeah, and on Earth, because the Earth is rotating, we have two components of gravity. One is centripetal. There is a reason we stay on the Earth and not just gravity. We also have centripetal force holding us to the Earth. So those two forces together make up gravity. So in summary, centripetal force, Coriolis effect, friction, gravity, all impact the motion of air parcels. So let's take a look at one. Hydrostatic equilibrium. So yeah, we have gravity pulling the air down. We have the Earth rotating. We have a pressure gradient that's in the vertical, and a pretty doggone strong one in the vertical. Why don't all the air parcels just fly out into space? There's an equilibrium that's established that an air parcel will stay exactly steady in one spot when the pressure gradient is balanced with gravity pulling it down. That's called hydrostatic equilibrium, and the air is normally in hydrostatic equilibrium. Doesn't mean an air parcel can't move. If that air parcel hits a mountain, it's going to go up. If it goes on the other side of the mountain, maybe it'll descend some. But it's always going to move at a constant velocity if it's under hydrostatic equilibrium. Now, to make things simple, we think about geostrophic winds. Geostrophic is pretty much just a straight wind. It only really deals with two forces. It has the pressure gradient, which starts the parcel in motion by moving it from high pressure to low pressure. As it begins to move that way, Coriolis force starts up to the right. So now that's bending that air parcel. It's going more and more to the right till finally it reaches a balance. The pressure gradient and the Coriolis force are balanced. No friction is involved here. This is above in the upper parts of the atmosphere, and this is a straight line wind. Now, around low pressures, high pressures, the air curves around them. So now we add centripetal force. So what the gradient, where we had geostrophic wind with just 2 components, the gradient wind has 3. It has the Coriolis effect, the horizontal pressure gradient, and the centripetal force. Those 3 cause air particles to move steadily around in a circle. And they can either blow clockwise or counterclockwise, depending on whether low pressure or high pressure. Now, friction. What's it do? Well, if I'm near the ground, we have friction. Friction slows the speed of the air. If you slow the speed of the air, and Coriolis force is determined by the speed of the wind, the Coriolis force is going to get a little bit less. If that happens, you're not turning the wind as much to the right, you wind up with wind blowing at an angle across the isobars towards low pressure. So there's some convergence towards low pressure and out away from high pressure. So here you can see it. It's not directly into the low pressure, but it kind of works its way in, and it's not directly out of a high pressure. And this is due to friction in the lower part of the atmosphere. Now, wind is a continuous thing. If I impact the upper part of the atmosphere, I'm impacting the lower part of the atmosphere. So if I have a horizontal convergence upstairs, maybe 30, 40,000 feet up, that's going to tend to push the air that was there downward. As that air is hitting the ground, it's going to want to spread out, so you get divergence at the surface. That's how high pressures are actually formed. They start with the convergence aloft, and they wind up diverging at the surface. So you develop high pressure because the air is coming down and sinking into that area. Low pressure, the opposite. You wind up with winds pulling apart aloft. The air is going to want to rise up. Pressure is getting lower, and winds are coming in towards that low pressure, and these are tend to be bad weather systems. Now, if you look over lakes, and you're going to see a question in critical thinking of this, and have wind blowing across the lake, we'll say Lake Erie. As the wind's blowing across the lake, there's very little friction, so not slowing down. Now, as that wind's approaching the coast, say it's coming from the north, it's coming into the, right as it's approaching Ohio. What's it going to do? Well, there's a lot more friction along Ohio, the land, so it's slowing down. As it's slowing down, convergence is taking place. The air is going to want to rise. As it begins to rise, guess what? That causes your lake effect snow showers in the wintertime, and sea breezes, similar mechanism, can cause thunderstorms in the summertime. So with all that in mind, I just want one last thing to show you here. I wanted to look at winds aloft. Here is geostrophic wind. You see how parallel it is. So aloft, you have the geostrophic wind flow. So I hope you got something out of this, and let me know if you have any questions.